Hello, everybody. I hope you're all doing well. Welcome to installment 4 of apportionment videos. This will be the final video on apportionment. We'll talk about paradoxes that can arise and other things that might make an apportionment method good or not good. So we'll talk about that. A couple notes first. I think you'll all be pleased to hear that I've decided not to give any more exams. So there's not going to be another midterm, and there will not be a final exam. The rest of your grade will consist just of these online quizzes, and the first exam that we took, and a project which I will assign next Tuesday or Thursday, sometime next week. The project will be in regards to financial math, the section that will start on Tuesday of next week. So yeah, I hope you're all happy to hear that. But the project should be fun. I'm putting together some final little I'm tweaking it a little bit, and I think it'll be beneficial to, especially to those of you who wanted to be studying financial math, and we've been talking about political science all semester. Anyway, this is just the way it went. But today we're going to finish talking about political science. So apportionment will be done after today. Let me just make a couple notes of those things I said, and we can begin. Good. So, what's the date today? 3/26, March 26, 2020. No, 17. Notes. No midterm or final exam. Your grade will consist of exam 1, quizzes, financial math, project, assigned next week, due by last day of class. I think that we're still 4 weeks from the end of the semester, so I think that'll be plenty of time to do your project. I mean, you will have 4 weeks by the time I assign it next week. And so I thought I'd just make it due on the last day of classes, and then we won't have to worry about a final exam period or anything. Good. I hope that works for you. Let me know if it doesn't. Oh yes. So quizzes. I know I said that they'd be due on Thursdays, but I think it's easiest just to post them every Tuesday, make them due every Tuesday, and that way, especially given that I'm kind of assigning those quizzes based on a full week's worth of material, then I'll post the quiz on Tuesday concerning the previous week's material, and instead of making it due on Thursday, I figured I'd just make it due on a week give everyone a week. So I don't know what your schedules are looking like these days. I know that they're busy. So quizzes assigned and due on Tuesdays. You can all check the schedule. I'm posting a schedule this morning, an updated schedule, so all of this will be reflected on there. It should keep on Blackboard. So yes, check new schedule on Blackboard. Okay, good. So I'll decide how I'm gonna weight your grades then, and oh yes, possible extra project on graph theory. But because I know that I'm going to be getting to my graph theory stuff in the very last 2 weeks of class, so it doesn't really seem right to give you a proper project on that. But I don't know, if you want something to supplement your grade, to round it out, I might have everybody just do another small project just to keep us working on things here, because yeah, the quizzes will not be too time consuming. I mean, this should make your life quite easy for the rest of the semester, at least in terms of my class. I know that your other classes are probably a big pain right now. So anyway, we'll figure this out. Okay, so let's start talking about the final section of chapter 4. This is section 4.6 on the quota rule and apportionment paradoxes. Okay, so we've learned about the two methods that we're going to learn about. Your book lists a few more. I think they had 5 methods or so that you could learn about, 4 methods. But we've done our 2. They're the ones that I think are most important to our political system, to our understanding of our political system. But if you go into your textbook at the very end, right after section 4.6, there is a little historical section on our nation's history with apportionment. And if you're interested, that so note directly after section 4.6, your book gives a brief history of apportionment in the U.S. And I'm just telling you that because I find this, I actually had a great time learning about how this stuff has worked in our own country, and so yeah. So if you're interested in reading it, I know I'm also not the source of information, so you should, a history information. So yeah, take a look at that. It's interesting. Okay, so what's the goal? So what's the goal of this section? The goal of this section is going to be to explain a relatively recent result. So by relatively recent, I mean this was about 1980. That these two mathematicians came up with this result to explain a relatively recent result that all apportionment methods are inherently flawed in some way. All possible apportionment methods are inherently, I don't know how to spell this word actually now that I think about it. Oh, inherently. Sorry, I should have do not disturb on. Let me go and do that. That should have been done. Flawed in some way. So disregard the spelling of inherently. I should probably know that, but oh well. So this is a bit like Arrow's impossibility theorem. Remember, in our first chapter when we learned about all the different voting methods that we could use in our political system. We learned about all the different voting methods, and then we ended up with a result saying that every voting method that we have created or will ever create is flawed. This is a bit similar. Though I think, though if you ask me, these apportionment methods are flawed to a slightly lesser extent than, some of them are flawed to a lesser extent than some of the voting methods were. I think we really do have pretty good apportionment systems, but let me tell you what I mean by this. So, should relate this to Arrow's theorem from chapter 1. Okay. So if I say that they're all flawed in some way, what does that mean? So what would it mean for, the first question should be, what would it mean for an apportionment method to be fair? So good. What would it mean for an apportionment method to be fair? Or what would make an apportionment method fair? What would make? Well, this is when we get to our first, the title of the chapter. The first thing that people decided was the quota rule. Maybe not the first thing, but one thing that people have decided should make an apportionment method fair is the quota rule. So what is this? So 1, the quota rule. And what does this say? The quota rule states that every state should receive or should be apportioned either its lower quota or upper quota. So this isn't to say that every state should receive its lower quota or every state should receive its upper quota in a method. It's just saying one or the other. So what is here? I'll give you a little example. The example to think about is like, well, okay, so here we go. Example. So say your friend owed you $38.72. Say you owed $38.72. But your friend comes over and they've only got dollar bills, and so they say, well, I don't have any change, so you can either have $38 or $39, right? Maybe they're a little low and they only have $38. Maybe they have a $39th dollar and they offer to give it to you. Well, then you'd probably be pretty satisfied. You wouldn't make them go and find quarters and pennies to give you the 72 cents, right? So you would probably accept 38 or 39 if they didn't have change. But 37 would probably be too low. Too low. Especially if they had 38 to give. And $40 would be unexpected, right? Unless they only had 20s. And so what this means is like, so say you're a state, so say you are a state with standard quota. Remember, the standard quota was a decimal. It was the exact number of seats that you should be apportioned if we were allowed to give away fractions of a seat. 38.72. Then you should receive either 38 or 39 seats, is basically what we're saying. Not 37, not 40. And so why do we think this? So why do we think that this is a good rule? Because if you're like me, you might think that it sounds kind of arbitrary. But your book gives a pretty good explanation And that explanation is that the standard quota is supposed to be the true method, the true measure of how many seats you deserve. So 38.72, if 38.72 is the true number of seats that you deserve, well then any fair apportionment method should not differ from that standard quota by more than 1 seat. That's the idea, is that if it's a fair method, it sticks close to what you really do deserve in the true sense, 38.72 seats. And if it sticks close to that, then it shouldn't differ from that by more than 1 seat, because if you go in either direction by 1 seat, you pass through a whole number, and that whole number should have been given to you. So, why the standard quota is the true measure of a fair apportionment. Thus, any method, any apportionment method, should not differ from the standard quota by more than 1 seat. Good. So I've already expressed to you, I find this rule a little bit arbitrary. I think that it's one of the least important things that we consider in evaluating apportionment methods. And I'm not alone. So I'm not alone because we use the method of equal proportions in our House of Representatives, and the the method of equal proportions, or the Huntington Hill method, does not meet the quota rule. I'll show you why. So I'll say personally, I find this rule relatively arbitrary. Why only 1 seat? Maybe you'd accept. Maybe one should. So maybe we should have 2 seats. And ultimately, I think 1980 was not such a long time ago when they used these things to prove their. Belinsky and Young used these criteria to prove their theorem. I mean, 1980 isn't so long ago. There are still lots of open questions here, lots of questions to be answered. And so yeah, if I feel like this rule is a little bit arbitrary, maybe I could do something about it. Yeah. So why only 1 seat? I think that there are more important things to consider. Good. So, Huntington Hill example. Well, why don't I give you a good example? So Hamilton's method does satisfy. I'll give you an example and a non-example. So, an example. Hamilton's method. This was section 4.2. Satisfies the quota rule. And I'll let you think about why that should be. Well, let's think back to what Hamilton's rule said. So, Hamilton's rule gave every state with a quota less than 1 a single seat, and then that one was fixed. So any state with a quota less than 1, think about it. So any state with a quota less than 1 was given their upper quota. So they're good, and then we leave them alone because they won't get apportioned to the surplus seats. Okay? So now any state that had a quota bigger than 1 is given its lower quota, And then surplus seats are handed out one by one, and every state is only allowed to get one surplus seat. So then some of the states will have been given their lower quota, and some of their states will have been given their lower quota and given a surplus seat, so that's their upper quota, but nobody gets anything more or less than that. Good, so states with standard quota. I'm going to start abbreviating this SQ. Less than 1 are given upper quota and no surplus seats. And then any other state is given its lower quota and then at most 1 surplus seat, i.e. some receive their upper quota. Good. So that works. And now we're going to try a non-example. Here, I'll let you all write that. Now we're going to try a non-example. Because as I just said, Huntington Hill are equal proportions. Does not always meet the quota rule. And so to show you this, I'm going to do a counter example. So a counter example will suffice. Okay, so this is going to be exercise 65 in this chapter 4. I'm just going to do it out for you here because I think it wouldn't hurt to have another instance of Huntington Hill to look back on. It's also pretty funny, I'm not joking with you. Your book, your book defines it exactly like this. So, exercise 65, no joke. The small island nation of Margarita consists of 4 islands. The islands are Alita, Bonita, Corona, and Doritos. I kid you not, they are horrible at coming up with names in this book, but it did crack me up that this is our one example, and one of the islands was named Corona. Oh well, I hope you're all safe out there. The number of seats, okay. The number of seats, M, is 100, so we're saying in essence that they have a House of Representatives and we want to apportion those, so apportion these seats using Huntington Hill. Okay, so how are we going to do it? I will list the number of seats as M equals 100, populations below. So here, let me make a little table. Okay. So what I'm going to do here will be state, population, and what were some other things? Standard quota. Well, we'll figure out the other things we need as we get to it. But here we will do that. Here we will do that. I'll move this over here. I'll do it like this. Okay, so Alita, Bonita, Corona, and Doritos, and their populations respectively are 86,915, 4,325, 5,400, and 3,360. And in total, I've added these up already, added up to 100,000. Okay. So now, how are we going to calculate the standard quota? Remember, first we need to find the standard divisor. Is the total population over the number of seats. So remember, this is P. Total population there is 100,000. So this is 100,000 divided by 100 seats, which gives us a standard divisor of 1,000. Good. And so now that we've got our standard divisor of 1,000, our standard quota is just going to be the population of the state divided by the standard divisor. So that's population of the state divided by 1,000. And remember, when we divide by 1,000, we can just move the decimal point over 1, 2, 3 places for the 1, 2, 3 zeros in 1,000. Little trick from high school algebra. Good. So this standard quota will be 86.915, and this one will be 4.325. This one will be 5.4. This one will be 3.36. Good. Now, remember from last class, when we do the Huntington Hill rounding, Huntington Hill HH rounding rule, if standard quota is less than the geometric mean, and remember that was the square root of the square root of the lower quota times this upper quota, right? Square root of the lower quota times the upper quota. Round down, otherwise round up. Okay, and I'll let you go back and look at the last video lecture if you don't remember what that is. But the standard quotas, so the geometric means, just to remind you, a geometric mean is always between 0.4 and 0.5. So that's always like a little bit lower. For very small numbers, it's closer to 0.4. So like the geometric mean of 1 and 2, if your standard quota was 1.5, then you would round up, or even if it was 1.45, you would round up because the geometric mean of 1 and 2 is 1.41, about root 2. And then it only gets closer and closer to 1.5 from there. So let's do H rounding. So luckily all of these standard quotas are either less than or equal to 0.4 for their decimal or bigger than 0.5. So we don't even have to worry about the geometric mean. We can just round. The Huntington Hill rounding will be the same as normal rounding in this case. Okay, so this one will be rounded up to 87, this one down to 4, this one down to 5, and this one down to 3. And what do we get? Well, when we add this up, we'll get 8 plus 4 is 12, plus 87 is 99. So remember what I said, that the standard divisor might not always work. So this is one of those cases. This is like the problem we had in section 4.1 when we tried to just use normal rounding. So let's change some things. Okay, so if we try making our standard divisor just a little bit smaller. So we need a new divisor. Try D equal to 990. Okay, so that's just a little bit smaller than 1,000. And I'll give you a hint. If I picked anything smaller than 1,000 and bigger than 900, it would work. So I want to pick something that's pretty close to 1,000. Maybe I should have even done 995, but 990 is pretty close. And remember, in general, I will give you all of that information. So here, why don't I just copy and paste this table so I don't have to write it all over again. Copy. Paste. So now, though, instead of, so we'll erase all of these bits because we're not going to be using the standard quota anymore. Now we're going to use, instead of the standard quota, we're going to use the population of the state, P sub I, divided by 990. Is D. So this is our adjusted quota. Okay. And lucky for you, I've divided all these things because dividing by 990 is not as nice as dividing by 1,000. So what happens when we divide 86,915 by 990? We're going to get 87.793 something. And here we're going to get 4.369 something. Here we're going to get 5.4545 repeating. Here we're going to get 3.3939 repeating. Good. Okay, and now when we use the Huntington Hill rounding rule, well, this one will still round up to 88. This one will still round down to 4. This one will now round up to 88, but remember before it rounded up to 87. Tricky. Okay, round that one down, 5.4545. Now we really should check to see is this one bigger or less than the geometric mean. Well, the geometric mean of 5 and 6 is the square root of 5 times 6, square root of 30. And I calculated that one out. That's about 5.477 something else. And so, since 5.45 repeating is less than 5.477 something, we're going to round this down. So this will get rounded down to 5, and this will get rounded down to 3. And what happens now? Now we have 5, and 3 makes 8, and 4 makes 12, and 88 makes 100. Perfect. So we have apportioned all 100 seats, and this works. Good. So this works. But what was it that I was talking about? Remember that this was all supposed to contradict the quota rule. Oops. So how does this contradict the quota rule? Well, remember the quota rule says that every state should be apportioned either its lower or its upper quota. But look, state A has lower quota of 86 and upper quota of 87, but it's actually apportioned 88 things. So A has lower quota, L equals 86, upper quota, U is 87, but A is apportioned 88 seats, and this is a contradiction. Good. Yes. So that's our counterexample. So Huntington Hill sometimes doesn't fit with the quota rule. Okay. So now that we've talked about the quota rule, we can move on to talking about paradoxes. Okay. So now, apportionment paradoxes. We have already discussed a little bit the Alabama paradox, but I guess that's the I'll talk about it again because I think it's interesting and very relevant. So 1, the Alabama paradox. I won't spend too much time on it because I've already talked about it. But so this occurs. What does this mean? The Alabama paradox occurs when a state is apportioned fewer seats simply because the total number of seats being apportioned has risen. When a state is apportioned fewer seats simply due to the total number of seats M increasing. When a state is apportioned fewer seats simply because the total number of seats increased. Okay, so you can check back on lecture 4.1 to see, oh sorry, that was in section 4.2. So the second video, but it was on our first class day that I talked about it. So check video on section 4.2. Okay, and it's worth noting that I know we only talked about 2 apportionment methods, but your book talked about 4, and out of those 4, the Hamilton's method is the only one which gives any of these paradoxes. So if you had thought that maybe Hamilton's method was good because it met the quota rule, I would argue that it's bad because I think these paradoxes are much more important than the quota rule is. Okay, so I will go back and I'll tell you. Why don't I tell you why this occurs? So it's strange that this occurs. Yes. Why does this occur? It occurs because when we increase M, we change the standard divisor. SD equals P over M. And so every state's quota changes. Okay. And when every state's quota changes, though, that doesn't mean that the decimal points will all change by the same amount. Moreover, every state's quota increases, but not by the same amount. So decimals are scrambled. Can be scrambled. And then rounding down or rounding up, and then different states might have higher residues than some. Higher fraction parts. Okay, so what I want to do now is go back to, I don't know if any of you read the pages that I posted on Blackboard from Bushmanders and Bullwinkles, but I thought I would go back to that little example just to remind you of what I'm talking about here. I'll make a historical note. This paradox didn't necessarily come into place because so we didn't notice this paradox in our actual system. We so the House in 1882, they were debating different apportionment bills in the House. The House was debating different apportionment bills. And it was noticed that if the number of seats if the number of seats in the House was 299, M equals 299, Alabama would receive 8 seats. But if M equals 300, if they added just one more seat, Alabama would receive only 7. Okay, and so what does this look like in real life? Here, look at this table. So this is fictional. We just have 3 states, A, B, and C, A, B, and C, and their populations are listed here. They're pretty similar populations, except for state C, which is probably representing Alabama. Yes, indeed. So, similar populations of A and B, slightly different for C. Here are their exact quotas. When we sum up the populations, we get 1 million. We divide, we move the decimal point over 1, 2, 3, 4, 5 places. No, 1, 2, 3, 4 places. By dividing 1 million by the standard divisor of by dividing total population by the number of seats, 100. You get 1 million divided by 100 is 1,000, and so you move the decimal point over 4 places. You get exact quotas: 45.669, 44.668, and 10.663. So when we round each of these down, we get 45, 44, and 10, right? But that only gives us 99 seats. So when we want to give, who are we going to give it away to? We're going to give it away to the person with the highest residue part. That's going to be state A. I should have been looking down here. Still, sorry. A, B, and C, populations here, exact quotas here, same kind of calculation, but slightly different numbers. So now C has the highest fractional part, right? 0.337 is bigger than 0.331 and 0.332. So having rounded everybody down, we now give 1 extra seat to C, 44 and 45 go to A and B, and we apportion all 100 seats. We're good. Now, say that the number of seats in the House were to rise from 100 to 101. Now our standard divisor is going to change. So now our exact quotas add up to 101. That's good. But see how the decimal parts are different here than the last digits there. We're not just dividing by 1,000 anymore. Now we're dividing by 101, a standard divisor which is a little different. Still get this, 10, 44, and 45. Our lower quotas are the same. But now look at what happened. Because when we divided by a different standard divisor, our decimal bits changed. Now A and B have higher decimal point, have higher fractional parts than C. Whereas before, when their populations were exactly the same, nothing changed about their populations, just the number of seats. And so now states A and B have the highest residues, so they get the seats, and C only gets 10 seats. So this is exactly what happened to Alabama. And we have, with 100 seats in the House, Alabama was apportioned 11 seats, or state C was apportioned 11 seats. And with 101 seats in the House, it went down to 10. This is paradoxical. This occurs actually, and it wouldn't be so difficult for this to occur in real life. And so we took it seriously, and we don't mess around with it anymore. Good. So that's the most important paradox. I really recommend that you go back and read that section that I was just showing you, and also go back and look at the example that I did in section 4.2, because it's going to be helpful. Good. I have a couple more paradoxes to talk about. I won't talk about them in as much depth as the Alabama paradox, but because they haven't actually occurred in real life to as much of an extent. Okay, so the second paradox is called the population paradox. Again, this can only occur under Hamilton's method. It's Hamilton's method that does all this funny math of the rounding down and then taking the largest fractional parts. That just messes with stuff. So that's basically my point here, is that even though we have to change the divisor sometimes to make Huntington Hill work, all this strange dividing, rounding stuff in Hamilton's, using the fractional parts just throws everything off. Okay, so what is the population paradox? This is when a state is apportioned fewer seats simply because it's oh no, I should write that better. Population has risen. Okay, I'll just flip to the textbook to show you about that. I recommend going and reading this. Again, let me know if you don't have access to a textbook yet. Figure that out. But here, this is the one your textbook gives. I didn't want to write this whole table again, so I thought I would just go through it like this. In the year 2525, the 5 planets in some galaxy sign a peace treaty, blah, blah, blah. So we have 5 planets, A, B, C, D, and E. And they have populations in billions, I guess. 150, 78, 173, 204, 295. Total of 900 billion population. So, what are we going to do? They calculate the standard divisor, right? Standard divisor is given here, 18 billion. Divide the number of seats in the house. So they want to have, there were 50 seats apportioned. So maybe I'll write this in the margins. So M equals 50, SD equals 18 billion. And using that, we can calculate the standard quotas. So they've done that for us here. We get when you divide 150 billion by 18 billion, you get 8.333, 4.333, etc. And look at that, standard quotas always add up to the total number of seats in the house. We give everyone their lower quotas, and we're left with 2 surplus seats, right? Left with 2 surplus seats, those are going to go to which people had the highest fractional parts. Don't be distracted by the bold here. It was Coney and Elysium that had the highest bits. Others all had 0.33333. This one 0.611, this one 0.3888. Okay, so we give them the last seats, and Hamilton's method tells us that this is our final apportionment. Good. Everything seems normal. But now, they say after 10 years of peace, all was well in the Intergalactic Federation. The only thing that's changed is that we increase 2 of the planet's populations. We're going to increase the population of Coney, and we're going to, by 1 billion, sorry, the population of Coney goes up by 8 billion, and the population of Elysium goes up by 1 billion. This is represented in this table here. So remember, this is Elysium and Coney, which went up plus 1 billion, plus 8 billion, plus 1 billion. Okay. So now that their population, this Coney went up from, anyway. went up 8 billion, Elysium 1 billion. Now we take their standard quotas. We go 8.25, 4 point blah, 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 still add up to 50. Take their lower quotas, and we still end up with 2 surplus seats because it only sums to 48. But now let's look at who has the biggest decimal parts. Well, before, who was it? Before it was Coney and Elysium that had the biggest decimal parts. Now it's Coney and who? And Beta. Okay, so now B and C are apportioned our surplus seats. And look at this. Even though Elysium's population went up by 1 billion, they're now apportioned 16 seats instead of 17 seats. This is the strange thing. So this can occur. It occurs very rarely. This is a much more rare paradox, but it happens. So, good. See example on page. What page was that on? 121. Okay, and the final paradox I'm going to talk about is the new states paradox. This isn't one that actually happened to us. So that's interesting. We like ones that actually happened to us. Historical note is that in 1907, historical note, in 1907, Oklahoma joined the Union. And so when Oklahoma joined the Union, I'm gonna actually here. Give me a second. I don't want my thing to die. So unplugging that. Noises will get louder probably because of the fan going, but it's better than my thing dying. Okay. So in 1907, Oklahoma joined the Union, and sorry, where was I? We added 5 seats to the House to make up for, we didn't want to take seats away from anyone else because somebody joined. So Oklahoma joined, we figured out that they would deserve 5 seats by their, standard quota. We calculate everything, calculate the standard quota, give them their lower quota. We say, okay, so we'll add 5 seats to the House when Alabama joins. But when we recalculated using Hamilton's after they joined, afterwards, Maine's apportionment went up by 1 seat and New York's went down by 1 seat. Maine's apportionment went up by 1 seat and New York's went down. This is surprising. So because Maine and New York, they have nothing to do with Oklahoma. And we thought that we were calculating it well. We said, okay, Oklahoma has this population. Let's give them 5 seats because 5 seats corresponds to their population. But then when we add them and we calculate everything, well, we find that our apportionment changes. So what is this? The definition of this paradox is that this is when a state's apportionment is affected simply by virtue of a new state being added. New state, along with its fair share of seats, is added. And your book gives again only possible via Hamilton. And your book gives a good little example of this, but well, I don't think it's the time to go through it. I can show you real quick. They do an example with a garbage company, and so when there were only two districts in the city, Northtown and Southtown, they with 10,450 homes and 89,550 homes respectively. Now, using Hamilton's method, they apportioned 10 garbage trucks to Northtown and 90 to Southtown. But now they add a new district. So now there's Newtown, Southtown, and Northtown. Nobody moved away from Southtown. They just added 5,250 homes to make a new district called Newtown. And so because that quota was 5.24, should definitely be rounded down, they added five trucks. But once they recalculated everything here, we noticed that now Northtown and Southtown both get one surplus seat, and Newtown doesn't. Whereas before, only Southtown got the surplus seat, and Northtown's apportionment went down. So, look what happened. Southtown has now lost a seat. It had 90, and now it's gone down to 89, simply because Newtown was added. And that's not right, as they say. Good. So, I'm going to conclude, in conclusion, Huntington Hill violates the quota rule, but only sometimes. And Hamilton's method produces many worrying paradoxes. We don't like paradoxes. Well, I very much like to study them, but in general, we're not supposed to like them. So we stick with Huntington Hill equal proportions. Because it's the best we've got. And why do I say it's the best we've got? Well, it's because of this Belinsky-Young impossibility theorem. The ideal situation would be a method which satisfies both the quota rule and produces no paradoxes. But this is a mathematical impossibility. I'm sure the proof is quite interesting to read. I haven't read it, but it's a fascinating theorem. So this is kind of the overarching theme is the Belinsky-Young impossibility theorem, which states that any apportionment method that satisfies the quota rule produces paradoxes, and any method which does not produce paradoxes breaks the quota rule. Okay, so that is really a big theorem. I mean, it says cut your losses, right? Because we were searching and searching for a method that was just right, and it was only 40 years ago. Here, I'll put this around a little thing because it's the important result and it's stuck at the bottom of the page. Yeah, we were looking for a perfect method and it's provably impossible, which is okay, right? Because because not everything can be perfect, especially in our political systems. It would be embarrassing if there was a perfect method that we just hadn't found yet. So here is the mathematical impossibility. And just a side note, this is this theorem is 1980 by a man named Belinsky at SUNY Stony Brook and Young at Johns Hopkins. Okay, well, I hope that was helpful. Email me if you have any more questions. This is the end of our apportionment unit. Like I say, I do recommend reading that bit in the conclusion of this chapter, which talks about the U.S. history. I also recommend reading this book, Bushmanders and Bullwinkles, which I can show you right here if I flip my camera around. This is the book, Bushmanders and Bullwinkles by Mark Munir. And it's really interesting. Talks about gerrymandering, not just apportionment. Gerrymandering, which I didn't get around to talking about very much, but good. Well, that was